Hi, this is Laura, and these slides are from Chapter 10 for the geometry book that is published by McDougall Little, and this is section 10.1, parts of a circle and tangents. First off, we are going to talk about some terms, and we may go through a few examples later on. Be sure to pause and try the examples on your own before you check the answer. I will remind later. Okay, let's start off. Some things that you probably already know or may seem extremely obvious, but I'm going to point them out just in case there are a few of you out there who can't remember or don't remember or never had it. So, what is a diameter? The diameter of a circle goes through the center of the circle and it connects on each side. So this is the diameter. It goes through the center, sort of cuts the circle in half. The radius starts at the center, goes to any point on the circle. So there are many radii, and that is radii, the plural of radius. There is one radius, but there are many radii in a circle. And also congruent circles, which means they're pretty much equal, although congruent has a different technical definition. We usually use it in conjunction with being equal, but it actually means same size, same shape. So congruent circles have the same radius. Moving on. A few more terms. A chord is a line segment from one point on the circle to another point on the circle. You'll notice that it is not a line, it is a segment. It has two ending points. Therefore, a diameter is actually a chord. Also, there is a tangent, and it is a line, notice the arrows, a line that intersects a circle at exactly one point, which is called the point of tangency. And it might help you to remember tangent as touches. The tangent touches one point. Also, there is a secant. It is also a line, but it intersects the circle at 2 points. So a secant kind of slices. It slices right through the circle. The tangent touches, the secant slices, and the chord, well, I couldn't come up with anything clever for that one. So a chord is just a line segment that goes from one point on the circle to another. Now this seems way too obvious to even talk about, but it's mentioned in the book, so I figured I might as well bring it up just in case there's somebody out there who really can't figure this out. I'm going to be very obvious. There's an interior of a circle and an exterior of a circle. The interior of a circle contains all the points on the inside of the circle, and the exterior of the circle is all the points on the outside of the circle. So there you go. It's pretty much stating the obvious. Now let's try and use some of those things. You can pause now, and I want you to try and label all of the parts of each one of these circles. How many chords are there? What are they? What is a secant? What is a diameter? What is a radius? Which is a tangent? Go ahead and label those now. Pause. Okay, let's take a look here. What is a chord? PS is a chord, and PR is a chord. What about the secant? Remember, the secant slices. So the secant would be J. It's a line that slices off this little section. What about the diameter? The diameter is PR, and that is the only diameter. The radius, how many radii are there? There are actually 3, QR, QS, and QP. All of them are a radius or radii. Tangent touches, so what? And it's a line that touches, so K here would be the tangent. Okay, here is example 1, and this is a little bit tricky because you will notice, take note, that there is no line here. Now, I don't know, the book is a little questionable about this. Sometimes they're not consistent, but we have definitions that say that it is a line, and since there are no arrows that say that these lines continue on, we would assume that they are segments, line segments, and not lines. The book may do either. So pause now, and I want you to find each one of these. Okay, we're going to look at the answers here. And for chords, we have chord BH and AD. For the secant, now technically there are none because these are not lines, but a secant slices, and maybe because the book has in this picture a definite endpoint here and not a definite endpoint here, that they might say that, I don't know, BG is a secant, but technically if there are no arrows for me, then it doesn't mean, it means there is no line. So I would say there are no secants. Now AD, as far as diameter goes, is the only diameter. The radii are CA and CD, and the tangent here is GE, except again, there are no lines indicating that this, or no arrows indicating that this continues on forever. So I would actually say none for this one, that there are no tangents, although this line segment does touch. If these had arrows, then I would say yes, that is a tangent. Okay, so let's look at some of this information. First of all, you need to remember, here's a little reminder, what coplanar is. Coplanar means on the same plane. And remember that planes are flat and they go on forever in every direction. So here on the same plane, here we have two circles that intersect. They don't have any tangent lines or anything. They're just two circles that intersect at 2 points. Here in the red, there is one point of intersection. These circles are tangent. These circles are not tangent. These are tangent. This one is internally tangent. You can see one is inside the other. And here they are externally tangent. One is outside next to the other. So they have a common point of tangency. Also, here we have what are called concentric circles. They have a common center, but they have no points that are tangent. They don't touch each other in any area. So those are concentric circles. Now this is the tricky part. Here we have, if there is a common internal tangent, it intersects the segment that joins the centers of two circles. So this is really a little bit tricky. These, when you look at A, it's obvious that there is an internal tangent. One circle is inside the other. However, by definition, these are also internally tangent because it says that by definition that a common internal tangent intersects the segment that joins the center of two circles. Well, here's the segment that joins the center of two circles, and the common tangent intersects that segment. So that's why those two are internally tangent. Okay, let's look at the external ones because there's a little bit of trick there too. A common external tangent, these are very obvious because you can just look at them and you think you know. But here there are other common external tangents. It does not intersect the segment, this segment right here, but there's a point of tangency here and a point of tangency here. So this is tangent to both circles. That's an external, a common external tangent. They have that in common, that tangent. Let's look at these. Are the tangents internal or external? Based on what we've just seen, you should be able to do this easily. Pause the video now and check your answers. Okay, we're going to look at the answers on the next slide. And yes, we have external. These are externally, this common tangents externally. This is external too, just like the pictures we saw. And this one would be internal. Make sure that you know the difference because there will probably be on a quiz or something later on. And you don't want to be caught by the trickiness of those problems. Questions. Let's look at example 3. Given the center of the radius of each circle, describe the intersection of the two circles and describe all common tangents. Now, if you're not really on the ball or connecting all of your math from the past, you may not remember that when we use the coordinate plane, by describe, we mean use common points like x, y. So what is the coordinate of point A, the center of circle A, or the center of circle B? Also, when we talk about a line, remember, if it crosses the x-axis at 1, we use the description of x equals 1. So our description is going to be an equation, that x equals 1. Make sure you pause the video now and describe all of these things and check your answers in a minute. Okay, I'm going to show you the answers. Ta-da! So if we are going to check for A, the center of circle A is at 4, 4. The center of circle B is at 5, 4. The point of intersection is going to be right here, which is at 8, 4. And the common tangent right here where it touches, the point where they intersect, is going to be 8. So since it crosses the x-axis at 8, we say x equals 8. So these are the descriptors that we're going to use for those things. Moving on. We got some theorems here, and I kind of translated them for you. For theorem 10.1, you've probably heard this before. Basically, these are saying if a line is a tangent, then it's perpendicular to the radius. So if this is a tangent, then it's going to be perpendicular to the radius or a radius. Also, for the next one, it says pretty much the opposite. If a line is perpendicular to the radius, then it's a tangent. So if this line is perpendicular to the radius, then it's a tangent. How do we know if something is perpendicular? It's a 90-degree angle. Let's use it. Is EF tangent to D? Given what we just learned, what's the best way to figure this out? Think about a right triangle and the things we know for right triangles. Pause the video and try and figure that out. Okay, ready for the answer? I'm going to give the answer. Here we go. Whenever we are talking about right triangles, our most common tool is a Pythagorean theorem. So that's what we would do here, because we know that the hypotenuse is 61 and one leg is 60 and one leg is 11. Therefore, if it's true, there's perpendicularity, which means that this is a right triangle. So all we have to do is plug in our numbers, 11, 60, and 61, and see if they're equal. Is 121 plus 3600 equal to 3721? Yes, it is true. That means that EF is a tangent to DE. Another example. You're standing at C over here, 8 feet from a grain silo. So this is 8 feet, just this little tiny piece. The distance from you to a point of tangency on the tank is 16 feet. That's this one right here. What is the radius of the silo? So you want to find this, whoops, and this. What are you going to do to find that? It doesn't specifically say here for sure that it's a right triangle, but we are going to assume that it is in this case, and we can use the Pythagorean theorem again. Make sure you pause. Okay, I'm going to give the answer. Are you ready? Okay, this one is a little bit trickier because you have a few things to figure out. Now, because this is supposed to fit with what we're learning here, we did assume that it was a right triangle so that we could use the Pythagorean theorem. All we have to do is, we know what the hypotenuse is. That's obvious. Then we have two legs, except that we are missing one of them. So we're just going to plug in an r squared for that. And then we know that this leg right here, the hypotenuse, is going to be 8 feet, but we don't know this part. All we know is that it's a radius. It's going to be the same distance as this. So we're just going to call that 8 plus r. And it's going to have to be squared. So it's going to look like this. We've got r squared plus 16 squared equals 8 plus r squared. What does that mean? It means you're going to have to use the FOIL. So FOIL that side out. And now all you have to do is simplify using regular geometry, and you should end up with the radius being 12. If you got this wrong, make sure you go back and make sure that you did the FOIL correct. Or perhaps if you were adding and subtracting, you made some errors there. Sometimes we do that. We forget that we have to, I have to subtract it from both sides, and our brains screw it up and we will add it to one side, or just common arithmetic errors. So check your arithmetic there. Maybe you divided wrong, who knows what. So that's the first place you want to check if you got it wrong. Otherwise, go back and follow my steps and try again. We are ready to move on. Another theorem. If two segments from the same exterior point are tangent to a circle, then they are congruent. What? Well, if we use the diagram, then we can see that SR and ST, this says that these are going to be congruent if they are the same distance from the same exterior point. That would be S. So if these are the same distance from S, they are congruent. Let's use it. So, by the way, in the book, this is example 7, because example 6 is the proof of the theorem, and I'm not going to go through that. If you need to do that, you're going to have to check with your teacher. Okay, so we've got AB is tangent to circle C. AB, tangent to this circle at point B. We have that AD is tangent to the circle at point D. So can you find X given what we know about this theorem? What do you know about this theorem and about things that are congruent? All right, pause, do it yourself. Okay, I'm about to show you the answer. Ta-da! Now this is a little bit tricky here. Now if this was a distance, the distances are always positive, so then we get rid of any negative answers that we have. It can't be that. But this is not a distance. We are looking for what is X, and it's going to be squared, so that can be positive and negative. So basically, what do we know? We know that AD and AB are equal. So we can just set them equal to each other and solve for X, and it turns out X is plus or minus 3. Finally, here is a quick quiz for you. Can you answer these two quick questions? What do you use to determine if a line is tangent to a circle? What process do you use? Think about it for a minute before I tell you what the answer is. And number 2, what do you do to find the value of X given two tangents? What is the process that you go through to do that? For number 1, since we're talking about right triangles, we use the Pythagorean theorem. And for number 2, we're talking about equal lengths, so we set them equal to each other. Okay, that's the end of 10.1. I'll catch you later for 10.2.